Okay, let's get started here. Welcome to week 6. We are getting close to our midterm. I'll have a bit more to say about that in a moment. I'll save it all for when I have that proper slide there. This should be our last week of material, actual new material. There's one thing we might not fully explain or might just need a bit more practice on, which we could save until just the first class of next week. But then most of next week will be just review time. So this week we are linear programming. It's a big topic. It's kind of hard. So we're going to do 2 large examples of linear programming, one today and one in our next class. And then that will be at the beginning. And with the remaining time, we will be starting to talk about matrices again, but seeing a different thing that we can do with matrices, or a different way of thinking about them. They actually turn out to be a fairly versatile tool, and there's lots we can do with them. Not just what we did before. Okay. Right, so announcements. I've been getting a lot of emails about attendance stuff, which is fine if they're one-off things, but a lot of the questions are things I've already explained. So let's try to repeat that here. If you want to check your own attendance record, you don't need to ask me what your attendance is. You can check attend.wsu.ac.kr and sign in, and you can check for each day. So you can check for the class and then also click on something, and then you'll see the exact this day, this many blocks missed or whatever. So if you think there are problems with your attendance, tell me the specific day, and then we can go back and look at that particular day. But we're not going to tell you one by one every day what your attendance record is, because you can check that. Second, there were a bunch of people last week who were joining using someone else's link. So as I've explained, the links you got in your confirmation emails, they're custom, they are personal to each of you. Each one of you has a different one. That's the main way that we are tracking attendance. So you should always use your own link. You should never use anyone else's, and you should not be sharing yours with anyone else's. For some reason, if your friend can't join on one day and you have to share the link as a one-off thing, fine, but tell us. So you need to tell us that you joined with someone else's link and tell us who that person was. And then we'll look at their record and how long they were in the class, and we can use that to know that you were present. But otherwise, we don't know, and we'll be marking you as absent. If you think you need to use another person's link more than one time, you don't. You got your own link, use that. If you have problems finding that link, or you deleted the confirmation email or something, let me know. We'll get that resolved for you. But everyone should be joining using their own link, and you don't need to go back to the Smart LMS page at all because you got the email. So use that instead. I put another description of this on the Smart LMS to hopefully make this very clear, because people are still a bit confused. And that will eliminate some of the attendance confusion we've been having. Okay, so question, what if you are late for just like a few minutes? That's fine. When we look at the records, we see exactly how long you were in the Zoom session. If you joined a minute or two late, or you got disconnected halfway through because of an internet problem and you reconnected soon after, that's fine. We'll see the total time that you were in. That's not changing. we haven't really had issues with that that I've noticed. It's just the people using other people's links or asking me to check their full attendance record, but they can check that directly. Okay, if you have more questions, you can ask after class. We have more stuff to talk about. Next big thing is the midterm, which is in week 8. This is currently week 6, so 2 weeks from now, probably all of your midterms will be in that week. And the plan is for Monday, October 18th. At that time, I'm going to book an actual classroom if we can do some people in person. But currently, I don't have any more information than you do about that. So currently, we have to prepare for the possibility that we will all still be online at that time and consider it that way. So if you're out of country, obviously, if you're in country, then possibly you could be in the classroom doing it. So it's everyone at the same time, all the students, all the sections at the same time. So that's why it's not in our regular class time. We also need more time than that. I've scheduled 3 hours for it. That's how much time you should have available on your schedule. The actual you doing the exam time is less than that, but technical problems, page scanning, whatever, takes a little bit extra time. So we have some buffer there. Just like the homework, your handwriting, scanning your pages, uploading a PDF. That's the basic idea. You're going to be live on Zoom with your camera and everything while we do that. I'm going to give you a whole bunch more explanation and detail in our next class, okay? But for now, just that's the basic thing. That's the time, that's the date and the time. Make sure you've blocked that out. If you have a part-time job or something, switch shifts with someone else. Make sure you're available at that time. Okay. Class conflict. Someone is telling me that they have a class until 7 p.m. on the Monday. Our actual exam time will start at 7. From 6:30, that's people joining and getting tech stuff figured out. Our actual planned start time is 7 o'clock. So for Riho, that shouldn't be an issue for you, as long as your previous class doesn't end like exactly at 7 o'clock. It's like 6:55. That should be enough time for you to join. If anyone does have an actual conflict, for all the first semester students, there's no conflict here. If one of you are like an upper year student and you have a specific conflict, I think I checked that and I'm pretty sure you don't, but if there is an issue with that, then let me know. Okay, lots more information will be shared about that later. For now, we need to go on with our material. So linear programming, which again is our kind of big, like sort of new thing for all or most of you. Vocabulary constraints, those are the limitations on our problem. We have feasible regions, which just show just on the graph, the colored in area, the shaded area that shows all the possible solutions, and also shows us what points are not possible solutions. We have the corners of that feasible region. So it's the intersections of the constraint lines will make those corners. We have some sort of objective. We want to maximize this or minimize that, and maximize profit or minimize cost or whatever and we use these lines to represent that objective with an ISO profit line or ISO cost line or ISO revenue line or ISO whatever, ISO function line. All right, and then we find an optimal solution, so just the best solution. I'll repeat the process here. I know I've shown you this slide before, but then we're going to do exactly this process for today's example. So identify the variables that work to best describe the problem. So identify variables, make equations, inequalities for all the things using those same variables. Put everything on a graph. Look at the graph and find what areas actually possible and what the corners are of your shape, the feasible region. And then you find which corner is closest to your objective function, your ISO whatever line. And we do that by, we want a line that is close to, but outside the feasible region. So close enough that we can just see the distances, and then that one will be the best. And then we can do a bit of algebra to solve for the exact point of intersection there, and then that'll give us our solution. So that's the basic idea. Identify variables, put everything on a graph, understand the graph, the shape and the corners, and then find the best corner. Okay. So let's do this. This is a minimization example. Our previous one was about maximization, but we can do linear programming in both directions. Take a moment and just read what's here, and then we'll start by trying to identify variables. All right, so our solution is about vitamin somethings and then trying to get some minimum amount of vitamins for some kind of food. Maybe we're like making some like protein shake to drink after exercising, or that we're putting vitamins in our dog's food or something like that. So I went to go grab this from my kitchen, just a little kind of bottle like this, put in the little drops of vitamin, whatever. So that's the kind of thing we're talking about here. All right. So we look at our situation and we have a bit of a chart here. Can anyone see or suggest possible variables? That's the first thing. What things can we play with? What numbers are flexible? And that we could potentially use to create variables to describe the situation?
X and Y.
Okay, so supplement X, supplement Y. Can you be a bit more specific about exactly what the variables would represent?
Number of supplement X and number of supplement Y consumed, maybe.
Number of X, number of Y. What is our way of measuring those?
Amount of X and Y in milligrams.
X and Y are not being measured in milligrams. The vitamins are being measured in milligrams.
Oh,
Which means they will be
drops.
They will be representing the amount of vitamin.
Something like this.
Drops.
Okay. So actual drops. You'll just squeeze. How many drops of whatever thing are you going to squeeze out, like in the food or in the smoothie or whatever? So that's the thing that's flexible. Let's go to the next slide here, and we'll kind of see that. So it's a little easier to see here. I've sort of made the chart a little bigger. So we have two different kinds of supplements, and we want to put, we want to have some combination of how many drops of this one and how many drops of that one in order to reach some sort of minimum amount of vitamin stuff. So for vitamin C, it's telling us we want to, so again, in our food, in our dog's food or whatever, we want to have at least 600 milligrams of vitamin C. And for vitamin D, we want at least 360. For vitamin E, we want at least 40. Some like daily nutritional requirements or whatever. So we're trying to get that. And then we've purchased, or we have available, two different supplements. And okay, so supplement X, so little dropper thing for X, 1 drop of that contains 20 milligrams of vitamin C and 10 of D and 4 of E. And the unit cost, like per drop, it's costing 5 cents. All right, and then for our supplement Y, it's the same thing. So kind of a different amount. So Y has more of C and more of D, but it has less of E. And then we want some combination of these things to give us a total 600, total 360, total 40, but in the lowest possible cost. So what combination of X and Y will give us these minimum daily amounts while achieving the lowest possible cost? So of course, if we didn't care about the money, we could just say, let's do, I don't know, let's do like, just don't do drops, just dump the whole bottle of X and whole bottle of Y in, and then we'll get the amount. Like we'll be over, but whatever, we'll hit the minimum and we're fine. But that would cost a lot more money. So we don't want to do that. We want to find a better way of solving this. Okay, so how many drops of X we will use and how many drops of Y we will use, that's the thing that's flexible. That's the only thing we can actually change. We can't change how much vitamin C is in each drop. It's just that the thing's already made. We can't change how it's made. Or how much vitamin C is in the other one. We can't change the minimum daily amounts. That's just, you know, basic nutritional requirements. We can't change the cost per drop. That's just whatever the price of the thing is. So the only thing we can change is how many drops of this one do we squeeze in, how many drops of the other one do we squeeze in. So when you're identifying your variables, identify the thing that is actually variable, the thing that you have flexibility with. So how many drops of X, how many drops of Y? All right, so that's the first part, but then we also need to make sort of our constraint inequalities and some sort of function for our objective. So how could we do that? I'll write this here. X, number of drops of thing X, and same for Y. How many different limitations, how many different constraints do we have in this problem?
3.
3. What are they?
20x plus 30y is greater than or equal to 600.
Okay, so you're telling me the exact inequality. First, I just want to say, so it's vitamin C, vitamin D, vitamin E. So we want to have a low cost, the minimum possible cost, but we have these 3 things, vitamin C, vitamin D, vitamin E, required amounts that are forcing our costs up. So something's forcing us up, but we want to still try to find the lowest possible one. All right, and Vincent just told us the first inequality, which will be 20 times X plus 30 times y is less than or equal to 600. So hopefully we can see this because X is number of drops of vitamin thing X. So 20 times X gives us the amount of vitamin C total from X. 30 times Y will give us the total amount of vitamin C from thing Y. And when we combine, sorry, not less than or equal. Let's fix that. We want that to be greater than or equal. So 600 is a minimum. Over 600 is fine. If your body takes in too much vitamin C, it just wastes it. You just don't digest it. It doesn't kill you or anything. But less than that is a problem. So less than 600 is a problem. Exactly 600 is okay. Over 600 is okay. So greater than or equal. Okay, and we can see the exact same pattern for the other two. Vitamin D is going to be 10x plus 20y is greater than or equal to 360. And vitamin E here. What is our objective in this scenario?
Lowest possible cost.
All right, lowest possible cost. And how can we define that? So what kind of equation could we make?
5x plus 4y equals cost.
5x plus, no, that's not that. 5x plus 4y. So we want to minimize costs. And cost is calculated as 5x plus 4y. Okay, so we've just taken the charts and we've taken all the information in the chart and turned them into inequalities and equations. Right, so hopefully we can see where all of those things came from. If anyone has questions, please ask. All right, so next slide, I have just same information written a little more clearly here. Okay, so we also, for our constraints, we have included these non-negativity constraints. Remember, I can't put a negative number of drops of either of these things into whatever food, whatever I'm adding it to. So we just write that out as the math. X must be greater than or equal to 0, Y also greater than or equal to 0. Same as we've done for our other problems. Okay, so this looks like it is set up. A question that a lot of people ask me when we do linear programming is, this seems hard. Why are we doing this? Can't we do this whole thing without the graph, without this whole linear programming method? Yes, we can, but it would be a lot of extra work. Let's go through the problem, and then once we've done that, I'll be able to better explain to you why it would take a lot more effort. We'll see what we did, and then we can compare with what we would have had to do. So it is possible without the graph, but it's definitely more time consuming. So let's go to the next part here, which is just graphing it. So in our method here, we said identify variables and build the equations and inequalities, which we've done. So now we need to graph everything. All right, graphing, what's our method for graphing with standard form equations?
Find the intercepts.
All right, intercepts. So we could do this any way we want, but finding the intercepts is a pretty quick and convenient way of doing this. All right, vitamin C, what are the two intercepts?
30 and 20.
30 and 20. For vitamin D?
36 and 18.
36 and 18. And vitamin E?
10 and 40.
10 and 40. Okay. So let's hold back on the cost equation. We'll put this part on the graph first, and then we'll come back and do the cost equation part. All right, just trying to remember, making sure I matched colors and everything. Yep, okay. So let's just put these on our graph. Our first one in orange with 30 and 20. Next one, purple with 18. So we don't have 18 on our grid here. Just kind of have to make a best judgment. Looks like it's about there to 36. About there. And our last one in blue, 10 and 40. Like this. All right, for each of these inequalities, are we shading above or below them?
Above.
Above for each of them. Say we see the greater than or equal for each of these. Okay, so where is the feasible region? What part on the graph represents that? Let's see if you can tell me without doing the number labeling.
The big white space.
Okay, so this big open space that is above everything. This is the solution space for our problem. So all of these areas below, it's not this one, it's not this one, not this one, because all of these are below at least one of the inequalities. And we said, in this case, we have to be above all of them. All right, so we've done the graphing and actually, let's skip ahead to where I have the nicer looking graph here. Okay, so there's the graph. And can we identify the, feasible region there and the corners that we are dealing with in this situation? Where are the corners?
0.40.
0.40. Okay, so our vitamin E and the y-axis.
The intercept between vitamin E and vitamin C.
Vitamin E, vitamin C. So blue and orange here, okay?
Intercept between vitamin C and vitamin D.
Okay, here.
And the x-intercept for vitamin D.
Vitamin D here at 36. Okay, so if we've done the shading correctly, then identifying the corners, should be pretty easy. You just find the corners that touch that shaded part. Just make sure you've done the shading well. So we had a number of possibilities. All of these points here are points of intersection between different inequalities, and there are 9 in this case. But from putting on our feasible region, we can see that, okay, only 4 of those are actually possible. Forget all those other ones. So there's part of our that's part of our efficiency here. If we did not do the graph, first we would have to manually calculate the location of all of these intersections. We'd have 9 different ones to calculate. And then on top of that, we'd have to eliminate the ones that are not possible. The graph makes it pretty easy to say, okay, those 4 there, those are the best ones. Those are the ones we care about. The other intersection points we don't need to worry about. But without the graph, we don't know that. We'd have to manually test each of them back into each of these inequalities. And that would take time. So there's part of our time saving with linear programming. All right, our next thing we'll think about, we kind of got ahead of ourselves. So let's take a step back and try to graph our costs, our ISO cost line here. So again, this is one of the things that lots of people find confusing about linear programming, but we need a constant.
Choose a
and we are-
random constant.
Yeah, we're just going to kind of make one up, not totally random. I want the math to be easy. So I have a 5 and 4 here with the coefficients, and I want to be very easily able to calculate my intercepts. So choose easy numbers. And then second, I'll just kind of do an example here. Let's say we do 20. That's going to make the math really easy, and that would give me a 4 here and a 5. And I put that on the graph. So y-intercept 4, x-intercept 5. Okay, so look at what that gave us. That gave us just this tiny little line down here. It's pretty far away from our feasible region. We want something that's kind of close because it's easier to see which corner is the closest. So 20 made the math work out really easily, but if I compare the x-intercepts and the y-intercepts, here we had 4 and 5, and then look at all the other ones. These numbers are just way smaller. So I want here my intercepts to be kind of close to the other intercepts. They should be similar numbers. So 4 and 5, that's kind of too small, too far away. If it were like 400 and 500, that's just way too big. It's too far away. So easy math for calculating intercepts and kind of close to the other intercepts in the same region or nearby. That's the best choice. So what I did here, I guess 40 might have been a better choice, but I chose 50 on the next slide. So I'm just going to do that. So 50 would give us an x-intercept of 10 and a y-intercept of 12.5, 50 divided by 4. So we will put that one on our graph here. So 50 and those two intercepts. And that gives us the cost line, the ISO cost line that we see down here. So this dashed green line. Okay, so it's closer, maybe not perfect, but it's definitely closer to our corners, A, B, C, and D. And we can try to see which one might be the best here. So we have 4 choices for the best corner, the best solution. Can we eliminate any of these choices right now using this ISO cost line?
A and D.
All right, A and D, really far away. Those are clearly not going to be the best. Like B and C are both reasonably close. A and D, it's hard to even show. I'd have to kind of imagine the graph extending, but it's a lot further away. So not A, not D. So we just sort of wonder, okay, about B and C here. So I know it might look like B is closer, but maybe we've made some like withdrawing our graph. If we're doing this by hand, maybe it wasn't like 100% precise. Maybe we've just sort of, our lines are like a little bit off. So let's not really trust that. So B or C, okay? So let's put, all I've done here is zoom in. Everything's in the same location. I haven't moved anything around. I'm just zooming in on what we have. So maybe it's B or maybe it's C. And again, the way that we figure this out is we make a perpendicular line to the points and another perpendicular line. And we just look at those and we try to say, which one is shorter? Let's still say, okay, maybe it looks like B, but let's try to be a little more confident. Let's try to be a little more certain about things here. So if we do that, then I'm going to adjust my ISO cost line. So instead of 50 here for the constant, this is why we don't care about the this is why we can just kind of make up a number for the constant, because we can change it whenever we want. It's not really a big deal. So I'm just going to change it to 80 and then just recalculate my intercepts of 16 and 20. And then here is our new ISO cost line. And now let's repeat the process of trying to see which one is closer. Here's perpendicular line to B. Here's a perpendicular line to C. Now, which one looks closer?
B.
B. Okay, so now it looks pretty clear. If I am on a computer and I'm using graphing tools or just drawing tools like Zoom provides me here, I can just draw the line like this and sort of slide it over like this. Again, the math concept here is that the slope is not changing. If we change the constant in an equation, if we change the 50 to an 80, we don't change slope. We only change the location. We're just sliding it back and forth, just like this. So if we just slide it closer, what happens? Well, okay, eventually we would see that we would touch B first. Excuse me. If you are doing this on paper, you can just grab a ruler and just, it's hard to see, it's a clear ruler. And then you line it up with whatever your first ISO whatever function is, and then just slide it over. That honestly works. It might not feel super precise, and we can do some stuff here to verify the corner, but that's a way that you can just kind of easily see which corner will be the closest. So that's what we can do here. And our strategy, our way of making this easier for us, when we drew this ISO cost line, the constant is flexible. We can choose a different constant to just move the line closer. And if we have our intercepts that are kind of close to the other intercepts for the inequalities, then that tells us that we're close to, it's probably useful. If the intercepts are totally different, like very far away, then that line isn't going to be useful and you should choose a different constant. Okay, so B looks like it is our best point here. Let's erase all of that. Okay, so where is point B? What is the exact location of point B?
6 and 16.
Okay, so it looks like on the x-axis we have a 6, and on the y-axis we have a 16. So it looks like this is the point 6 and 16. How can we verify that? How can we know for sure exactly what those coordinates are?
Find the intersection point
Of?
the line vitamin E and vitamin C.
Okay, so point B, we can see it's where the blue line and the orange line are crossing. It's the intersection of vitamin E constraint and the vitamin C constraint. Well, here's the equation for vitamin C, and here's the equation for vitamin E. That's two equations, two unknowns. That's a very easy problem to solve here. So 20x plus 30y, and we are going to say equals 600, equals because we are on the line. We are not somewhere in the middle of the feasible region. We're not in the or greater than. We are in the equals part specifically. We are on the line, so this is functionally equals. So let's say this is our vitamin C equation here. And then if we have our vitamin E equation, so let's just do elimination. I'll take 5 times my vitamin E equation, which will give me 20x plus 5y, and 40 times 5 will be 200. Okay, so let's just very quickly, easily solve this system of equations here. 20, that's 0x, and here that's giving me 25y, and that's equal to 400. Okay, so 25y is equal to 400, so y is equal to what?
16.
16. Okay, that's exactly what our graph told us. That's great. And then we have our other one here, 4x plus 1y, so plus 16 is equal to 40. So 4x is equal to 24, so x is equal to 6. Okay, 6 and 16, that's exactly what it looked like on the graph, but now we've verified that. We just did a little bit of quick algebra. We know the exact location of 16. So, okay, all right. And if we were to solve this, then we just take this point of intersection for B, and we put this back into our cost equation here. So how much does it cost to do B? We have where B is, it's 6 drops of thing X and 16 drops of thing Y. So let's figure out our actual cost there. So 5 times 6 plus 4 times 16. And what does this equal?
94.
94. So 94 cents, which we said before, or the problem gave us. Okay, so that's the cost. This is the minimum cost to achieve this. That's the lowest possible cost to achieve the minimum amounts of vitamin C and vitamin D and vitamin E, these sort of daily requirements that we calculated. So this looks like our solution. It's 94 cents per day, and it happens exactly where we put 6 drops of this one and 16 drops of the other one. So here, this is our solution. Let's say, however, let's say we're maybe not 100% sure that B is the closest. Maybe we've drawn this by paper, on paper, by hand, and it just, we can't be 100% sure. We think it's not the corners, it's not A, it's not D, but maybe it's also C. I'm not sure if it's B or C. What could we do in that case?
Substitute the coordinate for C into the cost equation.
Right.
And compare.
So this is cost for point B, and we could do the same thing, cost for point C, and say 5 times, this is 12 and 12, so 5 times 12 plus 5, sorry, not 5, 4 times 12, and we calculate what that is. Can someone tell us?
60 plus 48, 108.
108. So $1.08. Okay, so that is our solution. That is what points corner C would give us for our total cost. And okay, so obviously 94 is less than 108. We're trying to minimize, so 94 is the better choice here. So we've confirmed. We knew it wasn't corner A or corner D. and we weren't totally sure if it was B or C. It looked like B, but we weren't feeling 100% confident. We did a little bit of algebra, and we've now verified, yes, C is better than B. Sorry, B is better than C. So if we're not totally sure, we can do just this sort of checking process to confirm and verify our solution here. So it's always possible to check our work with algebra. That's the other reason why just sort of like, sliding your ruler across a paper and making up numbers for the cost ISO function constants. That's why that's okay, because we can always verify and check our work later if we're not 100% certain. But we get a lot by having this visual understanding, and we can eliminate a lot of possibilities really quickly and get down to, let's say in this case, it's one of these two best possible points. It's a lot easier to check just 2 points than it is to check 9 different points, which is what we would have had to do before. Sorry, we would have had to do without the graph, without the linear programming method. Okay, so that's the solution here. If we came back, let's erase all of this stuff. So our minimized cost was here at point B. Erase everything else. At point B, and it is exactly 94 cents. So maybe this doesn't feel like a whole lot of money to be saving, but if you're giving this food to whoever like every day or something, or it's your own like nutritional stuff every day, well, okay, that turns out to be, a significant cost saving over the span of a year. Or maybe we're making meals for 100 different people. And then, okay, if we can save 10 cents per person, or per meal, making 100 of them, or making 100 of them every day, okay, it turns into cost saving. This is a lot of what businesses do. Small efficiencies like this, and then with many repetitions, they end up giving you large overall savings. I hope as I've been explaining this, I've kind of been telling you why this linear programming method can save you a lot of time. If you don't fully believe me, I'll just do a quick little description here. So at the start of this problem, if we never used a graph and we wanted to solve this, we can. But here we have 5 different inequalities. So five different things. So that's a bunch of different points of intersection here. This is actually 10 different points of intersection, because vitamin C intersects with vitamin D, vitamin C intersects with vitamin E, D intersects E, and then also C intersects X and Y, D intersects X and Y, and E intersects both X and Y. That's a lot of different points of intersection. So again, it's 10 or 9 if we're doing a minimization problem. So 9 different possibilities. We don't know which ones are even possible. So we'd have to calculate those locations and then put those locations back into the other inequalities and test if they satisfy those inequalities. And then we would figure out what the corners are. In this case, we had 4 different corners. So that's a whole bunch of work just to do that part. And then which is the best corner? And without a graph, we can't narrow down to this one or maybe one of these 2. We'd have to check each of the corners in our objective function. We'd have to test all 4 of them. If we had a bigger problem with 5 or 6 or 7, like more constraints, more inequalities, then that very quickly becomes a lot more work. So it does save a lot of work. If you still don't believe me, if you're still not convinced, you can try some of the review questions I've recommended and try to do them without the graph. It's possible, but you'll see the time saving if we can just be a little bit clever, figure out some strategies, and we can solve these better. Okay, so that is linear programming minimization. So we can minimize, we can maximize, now we can also minimize. We'll have one more example of these in our next class where we're going to add one more sort of extra challenge to it. I will also go over more of these, at least one more of these questions in our next workshop. So there'll be more practice there as well. I did go over one in the previous workshop, and then we'll do more in the next workshop. Okay. If anyone has questions about linear programming, feel free to ask. Okay. Let's move on to your other favorite topic, matrices. So this is going to be the other thing that we do about matrices. Matrix elimination was one technique, one thing we can do with this tool called matrices. There's a whole other set of things, all kinds of other matrix operations, which is actually the bigger field with this. So what we're going to do now is an introduction to this other big way that we can use matrices. So as we've seen before, matrices, we can write them with these curved brackets, curved parentheses like this. We can also write them with square brackets like this. Usually, if we have to give a matrix a label, we would give them a label with a capital letter. So capital A here, capital A here. All these four on the top are the same thing. They're just written slightly differently. Matrices can be all kinds of different sizes. So we could have kind of tall ones like this, or very one column, but lots of rows like this, or it could be one row and lots of columns, all kinds of different shapes here. Okay, I see a bunch of people have to leave for PCR tests. That's fine. I hope you have a negative result. A good result, but like negative as a negative for the coronavirus. Matrices can appear in, again, lots of different sizes. We see capital letters B, C, D for these. That's just sort of convention. It lets people know that you're dealing with a matrix and not just some basic kind of variable. All right. So before, we always just kind of saw these like 3 by 3 with then the one extra column, but matrices can be all kinds of different shapes. We will talk about a bunch of different properties of matrices. So some kind of basic properties and some types. And the main thing that we are doing is talking about matrix operations. Most of these will not be too hard. Matrix multiplication is going to be the tricky one. We will not get to that today, but we'll get there soon. Okay, so let's start here with dimensions. When we talk about the size of a matrix, we always talk about the rows first and then the columns second. So this matrix A here has 1, 2 rows, and then it has 1, 2 columns. So I know they're the same here, but we can see this in the labeling on the positions. So this first position we could write as A11 because it's in the first row and first column. And the next position would be down here, A2, 1, because it's in the second row, first column. And then this one here would be A1, 2 because it's in the first row and second column. So it's a 2 by 2 matrix. Rows first, then columns. When we talk about a thing called matrix multiplication later, having the right order is going to be very, very important. All right, A here, it's the same as the other one. It's a 2 by 2 matrix, 2 rows, 2 columns. Let's try B here. Matrix B, how many rows, how many columns?
3 by 2.
This is a 3 by 2 matrix because 1, 2, 3 rows and 1, 2 columns. Matrix C, what are the dimensions?
3 by 1.
3 by 1 because 3 rows, 1 column. Matrix D,
1 by 3.
1 by 3 because 1 row, 1, 2, 3 columns. So the vertical measurement is coming first. So kind of how tall is it? And then the horizontal measurement is coming second. 1 and 2. Or rows and then columns. That's not right. How many rows? How many columns? If you remember, or as you understand, when we talk about coordinates and a grid, if we have an X, Y grid and I have some point here, we write this as X, comma, Y. Well, so the X is the horizontal, how wide is it measurement, and then the Y is the how high up is it measurement. So X and Y coordinates for just a graph with Cartesian geometry, it's Cartesian coordinates. That's sort of the opposite order. We do the left and right first, and then we do the up and down second. Matrices, we do it the other way. We do how big is it, how tall is it, the up and down first, and then the horizontal side to side second, with rows first, then columns. So it's kind of reverse, it's kind of backward, or the opposite of what we do for our typical graphing. So different, but you'll just have to remember that difference. Rows, then columns. Second thing, equal. To be equal, the matrices should be equal in every way. If we look at this matrix and this matrix here, we have the same dimensions. So this is a 2 by 2. Let's not do that one. We have a 2 by 2 matrix here. We have a 2 by 2 matrix here. We have the same values, 1, -1, 0, 3, 1, -1, 0, 3. All the same values, and all those values are in the same positions. So basically everything is equal. If anything about the two matrices are not the same, then they are not equal. If you remember when we did matrix elimination 2 weeks ago, then we did not write an equal sign between each of the matrices, each sort of separate matrix that we had in our process. This is why, because those are not equal matrices, we were changing them in each step. So equal means everything is the same. Even if they are very, very similar and there's just a slight difference between them, not equal. Must be equal in every single regard. Okay, so equal doesn't mean similar, it means exactly identical, the exact same, equal. All right, two basic properties of matrices. Two special kinds of matrices which we need to understand because we will encounter them. One is has the fancy name of the null matrix. Null just sort of means like empty or nothing. Also can be called a zero matrix. That's maybe easier to understand. A null matrix can be any size. It could be this size or it could be this size. Let's write these out. This is a 1 by 1. This is a 2 by 3. This is a 4 by 3. This is a 4 by 5. Any size is possible. And the basic property is that all of the values in it are 0. That might seem like it's not accomplishing anything, but there's actually there's a reason for having that and like talking about that in the math world. So I'll explain that in a little bit later when we get to the operations. So null means everything is 0. Null can be any size at all, but as long as everything is 0, then that is the null matrix. All right, the other type here, identity matrix. This one, again, when we get to operations, I'll explain why we care about this and why it's called identity. So identity matrix here. Okay, so first property, which you can see, they must be square. So this is a 1 by 1 matrix. This is a 2 by 2. This is a 3 by 3. This is a 4 by 4, ... 5 by 5, 10 by 10, must be square. What is the other key property of an identity matrix? What can you see here?
The number on the main diagonals 1.
Right, so the main diagonal, it's all 1. And what about the other positions?
0.
Right, they are all 0. So it's 1 on the main diagonal, 0s everywhere else. If you remember from matrix elimination, this was sort of our goal, getting this with the main part of the matrix, and we just had the constants over on the side. There's a lot of uses for this. There's a lot of reasons to go to this shape or start at this shape and do something else. So identity matrix actually has a lot of uses. So must be square, and 1s on the main diagonal, 0s everywhere else. That's what an identity matrix looks like. Okay, so let's just a quick review here. Dimensions, rows then columns. Equal means everything must be equal. Null matrix means just it's all 0s, could be any size. Identity matrix, and we can also sometimes see the term a unit matrix. It's the same thing. All mostly 0s except for the 1s on the main diagonal, and must be square. Those are basic properties of matrices. All right, let's pause in case people want to do a screenshot or something. All right. Second part, operations. This is the bigger thing to talk about. So we have lots of operations we can do with matrices, but these are the 4 kind of most core ones that we should all be familiar with. So transposition, addition, subtraction, scalar multiplication, and then matrix multiplication. So 2 kinds of multiplication to think about. First, transposition. So transposition is this, where we take some matrix here. So we see our positions 1, 2, -2, 4. And we take the whole matrix and we do a flip diagonally. Not horizontal flip, not vertical flip, not rotation. That's a mistake I see tons of students make every semester. They think it's just rotating the matrix. That's not what is happening. It is a diagonal flip. So what we see here is, so the 1 and the 4 on the main diagonal, those stay there, 1 and 4, but the other positions are getting reversed. So the -2 and the 2 are switching places here, like this. If we look at the next one down here, E, it's a little easier to see when it's not a square matrix. So main diagonal is 0, 0, 0, 0, and then the 1 and the 2 are flipping places. The 2 sort of flips down here. The 5 flips down like this. And we can see this here. So everything is doing a diagonal flip over the main diagonal. That's what's happening. That's the concept behind it, but it's a little easier to think about things instead just this way. To do a transpose, just take each row and rewrite each row as a column, and then you're done. That's the easiest way to think about it and remember it. So let's see what that would be here. Let's say for matrix E, row 1 is this. It's 0, 2, 2. So if I'm going to write out E, let's hide this thing here. There. So if I'm going to write out what E transpose is, I just take the first column, sorry, the first row, and I'm going to rewrite it as a column. So 0, 2, 2. First row becomes first column. And then I will take the second row, and I'm going to rewrite that as the second column here. 1, 0, 5. And that's it. That's all you have to do. Just take each row, rewrite as a column, and we have this transpose. We'll see why we care about the transpose in a little bit, but that's the idea. This gets used all over the place when doing matrix math with matrices. So we can take the whole thing and just sort of flip it. All right, let's do some practice questions with this. If you remember what I just said, take each row, rewrite as a column. Try to calculate what these things would be for me here. So take a moment, let's say, I don't know, a minute. This shouldn't take too long. Try to write out what is C transpose, F transpose, G transpose, given the matrices that we have here. Go ahead. Okay, let's try these out. So first, matrix C here. What are the dimensions of matrix C?
3 by 1.
So 3 by 1, 3 rows, 1 column. So if I do this transpose, how large or what should be the dimensions of matrix C transpose?
1 by 3.
Right, 1 by 3. The dimensions are just going to flip. So we'll have kind of a long and short matrix like this. Tell me what the 3 values will be.
5, -6, 15.
5, -6, and 15. We just took each number. So we took the row, we took each row and we rewrote as a column. And that's it. That's all we have to do. Let's do the next one. Matrix F. What are the dimensions for F?
2 by 3.
So 2 by 3. So if we do F transpose, we should have what size?
3 by 2.
3 by 2. Again, numbers are just flipping. So 3 by 2 is going to look about like this. What's the first row?
0, 1.
0, 1. Sorry, let's keep this consistent. We're taking the first row is F. we rewrite as a column. So tell me the first column of F.
0, 2, 2.
Okay, 0, 2, 2. And then the next column is just 0, 1, 0, 5. Just our second column here. All right, and G, what are the dimensions for matrix G?
2 by 2.
So 2 by 2. So G transpose will then be a 2 by 2, same dimensions. All right, this time let's talk, tell me the first row of G transpose.
3, 5.
3, 5, we're just kind of taking the column. And then the second row.
-2, 0.
-2 and 0, second one. So we can take each row and rewrite as a column, or we could take each column and rewrite as a row. We'll get the same result. So that's it. Transpose, again, I'll explain to you a bit later why we use this or how we use this, but for now, we're just doing a diagonal flip. It's a very simple operation. Okay. Giving people a moment in case they're writing. Transpose is not a rotation. Just if you put that idea in your mind, you look at F or you look at C and you think, oh, we just rotated it. Please erase that idea right now. We are not rotating, we are flipping. Okay, next thing is addition and subtraction. So this was one of the things I asked you to do for the preview. Let's see what we can think here. So let's say I have two matrices like this. I have this 2 by 2 matrix and another 2 by 2 matrix, and I want to add them together. What do you think? First, what will be the size of the resulting matrix?
2 by 2.
Okay. So also a 2 by 2. So we'll have need a bit of space here, but 1, 2, 3, 4 values, 4 positions. What's the first position going to be?
A plus E.
All right, A plus E, because we just took that position in the first matrix and we added that position in the second matrix, A plus E. And then it's the same thing for all of these, B plus F, C plus G, T plus H. So that's all we do. And subtraction, we do the exact same thing, except we're subtracting one value from the other value. So it's not really tricky. Like if you were to just take a random guess or take an educated guess and say, well, I think matrix addition will work like this. This is probably exactly what you guessed. And from the preview question, most people had that. So just match up the similar positions, combine them, and that's it. The condition here, the thing that we have to remember is that the two matrices must have the same dimensions. If the dimensions are different, matrix multiplication is not defined. We can't do it. So if I have these two matrices down here, a 2 by 2 and a 2 by 2, same dimensions, it's possible. We can do it. If I have these two matrices like this, they're really similar. Can I add these two together?
Probably after you transpose the other one.
If I transpose them, yes. What about right now?
No.
No, I can't add them together. So let's just do a quick little exploration here of what would happen if I tried to add these together. Let's take the first position and the first position, 0 plus 0 gives me 0. Let's take the second two positions. 2 plus 1 would give me 3. And let's go down here. 1 and 2 would give me 3. 0 and 0 would give me 0 here. And then I have a 2 and missing. So 2 plus what number goes here? There's no number, so we stop. When we do matrix stuff, if we're trying to do an operation and we kind of need to pull a number from a spot that's empty, we do not use 0. We stop. We say it's not defined, it breaks, we can't do this, this operation does not work. So we never pull a 0 from an empty spot like this. If it's a 0, then there will actually be a 0 written in that location. We never just like make up a 0 or something. So if your operation requires that you pull something from an empty area that's outside the matrix, just stop. The operation is not possible. Okay, so that's the why here. So that's why this doesn't work. So must be same dimensions. This one doesn't work. This one as well. We have the same number of columns, and hey, look, even the first row is the same for each of them. No, doesn't work. They must have the exact same dimensions. Okay, that's about our time, and that's the addition stuff. So we will come back in our next class and actually do some examples of matrix addition and subtraction. And then we will talk about the 2 multiplication things as well. And then, and before all of that, we will do our final big linear programming example. Okay, so we've done minimization with linear programming, a big minimization example. We'll do a big maximization example in our next class. And we can talk about dimensions of matrices, and we started learning some operations. We'll do some more practice with them next time. Review. Now we've kind of seen a fair number of these linear programming questions. So you might want to take a shot at some of these review questions in this Buglier 2004 textbook. Excuse me, again, it's these particular review questions. Some of those are easier, some of them are harder. On our classroom page, I listed very specific ones that I recommend that you try. The other thing, our main textbook, the Intermediate Algebra 2nd edition one, it has matrix elimination, but it doesn't have these other matrix operations. So matrix multiplication and stuff, it's just not included. So there's a different textbook, which also from the same website, OpenStax, free, just go download the PDF. And it's this particular section of that textbook. And then there are these practice questions about adding and subtracting and transposing that you can do now. And then there are more that we'll be able to do a little bit later. So these matrix operation stuff that we're doing, different textbook, but it's all posted on the classroom page. You can see the details there. Right. Because this is a recorded lecture, so with the attendance stuff with the other classes, these are the homework questions which we will have for the end of this week. Some of these I haven't actually shown you how to do them yet. That will be in the next lecture, but because the holiday yesterday, this is where I'm kind of officially telling you what the homework questions are. So you might want to take a screenshot of this, and then and then actually try the questions a little bit later, just kind of save that information. Okay, I think we're done. If anyone has questions, please stay and ask. Otherwise, I will see you in our next class on Thursday, and I'll have lots more information about the midterm available for you then. Goodbye, everyone.